So we have the propagation through distance and the effect through distance. And later we want to have a different formula, and this formula says, of course, we can have a gain at the transmitter and gain at the receiver. And of course, initially we have the transmit power, and so that we have the receive power. And up to now, it seems to be we want to enhance it, so we have a gain. The gain try to amplify, to enhance it, but only gain. In fact, we have a loss. So actually, we have L. At L here, we have the accumulation of 3 possible losses. First of all, path loss. Path loss says, oh, as distance, as actually, if we have a distance, if you move and then longer distance cause the path loss. And then we have slow fading and fast fading. These cause to loss as well. So we have 3 different terms. And 3 different terms, why? L is the multiplication of the 3 factors. Because we want to accumulate. Well, maybe you have a question. Accumulate, but why it's the multiplication? Actually, if we talk about the real calculation, yes, gain, multiply. So loss actually divided and divided and divided. So we have 3 different terms. And if we have the different way to calculate gain and loss, for example, we can use log. If we want to measure loss or gain in terms of a log, then we will have a sum of the possible terms. But currently, they are absolute values, so we don't have any specific manipulation. Therefore, we have the multiplication directly rather than sum of all the terms. And in the exercise, sometimes we use dB, decibel. dB, then we can have the log included in the manipulation so that we can change the current operation into the form of sum. But right now, no, we have the original value or the absolute value. So we have the multiplication for all losses and multiplication for all gains. All right, so this one. And later we want to separate the 3 effects or 3 types of losses into the individual one, and want to check, or we want to investigate how to have the individual effect. Why we have the individual effect? Well, for the loss, we have the multiplication directly. So that way allow us to have the individual investigation. That's why we start from path loss first. You see what that means? Path loss. Signal strength decays exponentially with the distance d between the transmitter and the receiver. And this one we call the path loss because we have a path. As if we move further to leave the current, maybe it's the receiver. Move and to a different distance d, and then we will have a loss caused by distance d. And this kind of loss, of course, it is called path loss. And if we want to have the path loss under the effect of distance, then it's really simple. Let us have the transmitted power and over received power. Then we will have a loss. And if we want to have a gain, actually it should be received power over the transmitted one. But even we have that one, it doesn't mean 0 or none of the losses. So therefore, we investigate losses first. And this one actually, someone based on the field trials and saw that they can have some experiment result. Once they have the experiment result, they found some relationship. First of all, loss. The path loss actually related to distance only. Previously, it says yes, so we know the possible term causing by distance d. And only distance, no, this one still depends on frequency, carrier frequency. So if we have the large carrier frequency, then we will have a high value of path loss as well. Why higher than we have the path loss? If we have a high frequency, based on the formula, speed equal to frequency multiply wavelength. So high frequency, then we have a really short wavelength. Really short wavelength, then it will incur possible blocking by any buildings. So of course, if we have a large frequency, then we will bring the path loss for sure. But follow the current formula. All right, so we have this. And it says, well, if we have all these, depends on distance and also depends on carrier frequency. And then we have the path loss. And so that it says, oh, previously we just care about distance, but how about frequency? Yes, frequency depends as well. Therefore, we have a highlight here. And we also mentioned this one. Well, we know d squared, but don't forget, previously d squared for which model? Free space, right? And right now, if we have the communication, for example, in metropolitan area, and also consider a different scenario. Oh, okay, maybe we have a really wide area without any buildings, and if you consider that case, so since that one applied to free space, but right now if we consider metropolitan area, then it doesn't mean d squared, perhaps d squared to, for example, d raised power to 2.5, 3, and actually can be 4. If we have a d squared, it says, okay, the effect not so serious, but d raised power to 4, and this one is really serious. So this is an environment, for example, in metropolitan area, because we have many interferences, so that include those, and so that how about the loss coming from the path loss? Yes, even higher if we don't think d squared can reflect the facts. We will change it to d, for example, 3, and d 4. It's possible. So depending on the environment, then we will have the exponent of distance. So this one as well. And for the current formula, if we have a free space, why this one different from the previous one? In fact, this is the actually the field trial. Field trial, of course, we have the possible terms after trial. So this one, it should be the exact one, but the previous one is the simplified one. So the previous one, we do not have the formula like this. And here, we use it to serve as the path loss in free space. Well, again, we still have the path loss. And path loss d squared, no, right now we have d raised power to alpha. And alpha actually is the propagation constant. And the value for alpha, if we do not consider free space, normally we should have 3 or 4 for urban area. Right? I don't know, metropolitan area, we will have the severe effects coming from past loads. So of course, we should have the exponent rising from 2, for example, to the current one, 3 or 4 for the typical urban area. All right, that's it. So let me stop here temporarily and allow you to have the short discussion and thinking about currently what we reach and how we have the possible conclusions. All right, so maybe let me check the seats again. And for group 4, it's okay, just get closer. All right, so no problem, no need to change. And for group 1, yeah, you can get closer to have the possible discussion. And for Jen, your name Jen? Okay. Is it okay? Okay, sure. And feel free to have the discussion for the current items. And you can get closer. So I rather have 3 minutes to discuss, and later, if no question, then I can move on to the next one. Okay, so the current activity in the past are simply called turn and talk. And turn and talk actually allow you to have the chance to have further discussion with your teammates. And then you can refresh something and so that you won't fall asleep, right? So it's called a turn and talk, but that's a matter. I try to have a questionnaire. Do you think turn and talk efficient? They don't have any idea. And so that this time I didn't know the meaning, what that means, turn and talk. All right, so turn and talk maybe, oh, okay, don't waste time. Continue. If I continue, perhaps you fall asleep. All right, so even we can pause, allow you to have a chance to think. A chance to think. It's the pedagogy. All right, so even pause and then you have something to think. But let me check. Up to now, any questions? So if no, here, alpha 3 to 4, right, in urban area. And so that I have a question. How about alpha in a suburban area? Similar to 3 to 4 or lower? I can't call suburban area. Here it's urban area, so suburban area, it doesn't mean the free space. So that value should be comparable value like the urban area or a bit lower. To try to guess. Comparable, lower, or maybe higher. Which one you think? Lower. Yeah, lower. Okay, agree. So yes, it's true. If we have, if we don't have any, even no buildings, just trees, that's okay. So the value should be a bit lower, perhaps 2.5 or something else. But for free space, and then it's 2. All right, so this one. And the current formula, you see, it's the simplest formula. If we don't care about the others, we just care about distance. And then pass loads depends on distance. But previously, we have the formula depends on carrier frequency. So it doesn't mean purely depends on distance. But distance and the frequency are almost the same. They have the proportional way. So in terms of, first of all, in terms of the current formula, actually, all frequency and distance almost the same way, right? But dB actually it doesn't mean the pure quantity. We try to transform, for example, oh, okay, so the pure one, but we try to change it to, for example, and this one is called dB. All right, so dB actually will have a logarithm. Base is 10. And we have this and multiply 20. So we have the dB. And if we have log and multiply the previous one, so it should be, oh, this one multiplied the frequency and the distance. All right, so we have this. And actually, I don't know if we have the way to have the calculation. Perhaps we can collect sum rather than the multiplication. But we want to have the pure quantity. Based on the current formula, it should be the multiplication from frequency and the distance simultaneously. So both carrier frequency and distance affects the loads, the pass loads. So I emphasize dB